and absorbance of copper sulfate pentahydrate. The guiding question for this lab is, what is the quantitative relationship between absorbance and concentration for a colored substance? To answer this question, we did an experiment using a spectrophotometer. How to use a spectrophotometer. First, turn on the machine and wait about 15 minutes for it to warm up. Second, set the wavelength to 0. It does not have to be exact, but it shouldn't be far away from the number 0. Number 3, make sure that the compartment is closed and empty. Then adjust the percentage transmittance to 0% using the front left dial. Number 4, place a dry cuvette filled with distilled water into the compartment and adjust the percentage transmittance to 100% using the right front dial. From there, the spectrophotometer should be ready to go. Before we explain the procedures to this lab, there are a few vocabulary words that played a key role to this lab. Absorbance, the measured substance's capacity to absorb light. Transmittance, measure of amount of light passing through the substance. It can be found by this equation. Molarity, number of moles of solute per liter of solution. Concentration, amount of solute that is dissolved in a solvent. Spectrophotometer, apparatus for measuring time.
In this lab, we use many different materials. We use a weigh boat and a scale to mass the copper sulfate pentahydrate. We also use a beaker, volumetric flask, squeeze bottles with distilled water, a granulated cylinder, and a test tube or cuvette. In addition, we use a spectrophotometer to measure absorbance.
Methods. 5 molar solutions are made. Specific amounts of copper sulfate pentahydrate are masked for different molarities. To make a 0.3 molar solution, 7.48 grams of copper sulfate pentahydrate is used. For 0.25 molar solution, 2.46 grams is used. For 0.2 molar solution, 5 grams is used. For 0.15 molar solution, 3.74 grams is used. And for 0.1 molar solution, 2.50 grams is used. First, pour 100 milliliters of distilled water into a beaker. Second, fill half a volumetric flask with water. Third, add masked copper sulfate pentahydrate to a flask. Fourth, fill the volumetric flask to where the body meets the neck with water. Fifth, shake the solution until the solute dissolves. Sixth, use a squeeze bottle of distilled water to fill the volumetric flask until the meniscus rests on top of the line. Cap the volumetric flask and mix. Each solution is made before continuing. In labeled test tubes, each molar solution is poured into the corresponding test tubes. From these test tubes in a graduated cylinder, measure 7 milliliters of the first solution for a test tube or 3 milliliters for a cuvette. The test tube or cuvette that will be used each experiment should be cleaned before each use. A direction the test tube or cuvette goes in the machine is determined, marked, and used every time. The cuvette is put into the spectrophotometer and absorbance is recorded. Next, a blank, a test tube or cuvette filled with distilled water is put into a spectrophotometer. After that, the test tube or cuvette is put in the same solution and put in the spectrophotometer. The result is recorded and a blank is used again. This process of measuring the absorbance, using a blank, measuring the absorbance, and using a blank again is repeated for all of the solutions.
The independent variable for this experiment is the molarity of the copper 2 sulfate pentahydrate. The dependent variable is the absorbance. For graph 1, the R squared is 0.992. This graph shows a direct linear relationship with a y-intercept around 0. The points are generally around the trend line, some are above and some are below. This graph is also showing a directly proportional trend line and is a linear relationship. The y-intercept is noticeably above 0.
Conclusion. Guiding question. What is the quantitative relationship between absorbance and concentration for a colored solution? There is a direct linear relationship between concentration and absorbance. Beer's law states that absorbance is proportional to the concentration. This is proven true in this experiment. The trendline equation is y equals 2.64x plus 0.004 for graph number 1 and y equals 2.5x plus 0.036 for the second graph. The darker the color of the substance, the more light it will absorb. The lighter a substance is, the less light it will absorb. Beer-Lambert's law states that absorbance increases with concentration along with other factors. These other factors include path length and absorptivity. Our experiment verified this. Error analysis. Our y-intercept is too high. Also, the volumetric flasks were not filled all the way with water. This made the concentration of the solutions too high. This created a problem where the data was for higher concentrations than we anticipated. Lastly, the test tube might have not been clean. There could have been other particles in the container that had a higher absorbance. This would cause a y-intercept that was too high.